Hello, this will be a demonstration of Proposition 7 from Book 3 of Euclid's Elements, which states that if on the diameter of a circle, a point which is not the center be taken, and from that point straight lines fall upon the circle, the straight line on which the center lies will be the greatest, its remainder will be the least, and the straight line nearer to it will be greater than the more remote, and only two equal straight lines will fall from this point to the circle. All we are given is the circle A, B, C, D, like so. We are given its diameter AD, like that, AD, like that. We are given its center. We're going to call this E. We have a point on this diameter AD, which is not point E, and we call this point F. And from this point F, we have the straight lines FA, like so. We have FB, like that. We have FC, like this. And we have another straight line FG, like that. And the final goal of the proposition, the specification, will be to prove that FA, which is the straight line on which the center E lies, is the greatest and is greater than FB, which is nearer to FA than FC is, and FC being nearer to the diameter, or being nearer to FA than FG is, will also be greater than it. And the remainder of this diameter AD, which we call FD here, will be the least straight line falling from the point F. And furthermore, from point F, only two equal straight lines can fall from point F to the circle. We have a lot to prove, so let's get started immediately. The first things we do are that we join these straight lines BE, CE, and GE, like that. We can do that by postulate 1. Now, by proposition 120, that if any two sides of a triangle be added together, they must be greater than the remaining side. We know that the straight line EB plus the straight line EF must be greater than the third straight line BF. So if we look at this triangle BEF, we're adding the two sides EB, EF, and they will be greater than the remaining side BF. This is again proposition 120. We also know that AE and BE are equal. We know this by definition 115 because they are both radii of the same circle. And so we can substitute the EB here for AE so that we can say that AE plus EF, which is the straight line AF, if we add AE plus EF, we get the whole straight line AF. We can say that AF is greater than FB. This is the first part of our specification proven, that AF is greater than FB. Now, we also know that BE and CE are equal by the same definition, definition 115. We also know that the angle CEF being a part of the angle BEF must be less than it, and so we can say that the angle BEF is greater than the angle CEF. It's common notion 5. And if two triangles have two sides equal to two sides, and the angle contained by the equal sides be greater than the other, then the base of the one triangle will be greater than the base of the other. That's proposition 124. And so we can say that the base which subtends the angle BEF, namely BF, is greater than the base subtending the angle CEF, namely CF. So we can say that BF is greater than CF, and in totality, by a property of magnitudes, we can say that AF is greater than BF, which is greater than CF. Similarly, we can prove that CF is greater than FG. That would look something like saying that EC and EG are equal to each other by definition 115. We know that the angle CEF is greater than the angle GEF, for the angle GEF is a part of the angle CEF. And by proposition 124 again, we can say that CF is greater than FG. And again, in totality, by a property of magnitudes, we can say that AF is greater than BF, which is greater than CF, which is greater than GF. Finally, by proposition 120 again, we can say that GF plus FE is greater than EG. So we're now shifting to the triangle EFG. We're adding the two sides, GF and FE, and if we add them together, they must be greater than the remaining side, namely GE. We also know that EG and ED are equal. We know this again by definition 115, they're radii of the same circle. And so we can say that GF plus FE is also greater than ED by a property of magnitudes. And if we subtract FE from both sides, we can say that GF is greater than EF. So if we take the whole straight line ED like this, and we cut off EF, we're left with the remaining FD. Oh, excuse me. Oh, I wrote that down wrong. DF, like that. My bad. So we can say by common notion 3 that GF is greater than DF. Really bad D. Like that. And so again, in totality by property of magnitudes, combining all these inequalities together, we can say that FA is greater than FB, which is greater than FC, which is greater than FG, which is greater than FD. This is half of our specification proven. Now we shall move on to the second part, namely that from this point, only two equal straight lines can fall from it to the circle. We shall begin by constructing the angle FEH on the straight line EF such that it is equal to the angle GEF. This would look something like this. So you can say that the angle GEF is equal to the angle FEH. We can do that by proposition 123. And then we shall join the straight line FH, like that. It's again postulate 1. Now, we know that GE is equal to EH, again by definition 115, the radii of the same circle. We also know that the angle GEF is we know that the angle GEF is equal to the angle HEF because we made it that way in the previous step. And so we have the two triangles GEF and HEF having two sides be equal to two sides, namely EG being equal to EH and EF being shared, being common, and the angle contained by the equal sides also being equal, namely the angle GEF and the angle HEF. So by proposition 1-4, we can say that the triangles are equal in all respects, and the important respect is that FG is equal to FH. Now I will say that FG and FH are the only FH is the only straight line falling from the point F to the circle ABCD that is equal to the straight line FG. For if it is possible that another straight line equal to FG can fall from the point F to the circle ABCD, let's let that straight line exist as the straight line FK, and we will make it like so. Now, we know that FK is equal to FG because, well, that's the defining feature of FK. We said FK is a straight line such that it is equal to FG. We also know that FH is equal to FG. And so by common notion 1, we can say that FK and FH are equal to each other. Now we have arrived at the fact that FK is equal to FH, and FK must also be greater than FH, because we just showed in this step here, the first part of the proof, that any straight line nearer to the center from a point on the diameter that is not the center is greater than any straight line that is more remote. And FK we can see is nearer to the center E than FH is, and so we know that FK must also be greater than FH. So FK is simultaneously equal to and greater than FH, which is absurd. And so we can say that another straight line equal to GF falling from point F to the circle ABCD cannot exist. And so only two equal straight lines will fall from point F to the circle ABCD. Now, this being the final part of the proposition to be proven, we are done. Therefore, etc. QED. And for such a long proposition, the demonstration did not take that long, which I'm quite happy about. So I will end the video here and move on to Prop 3.8.